Welcome students once again into the class of number theory. In the previous video, we have stated and proved Gauss lemma, and now we are going to proceed ahead. The next theorem which I am going to prove, that write down the statement first and then we will move on to the proof. The theorem says if P is an odd prime and A is an odd integer such that their GCD of A and P is 1, then the Ligander symbol A upon P, Ligander symbol A by P is equal to minus 1 raised to the power T, where T is summation j vary from 1 to p minus 1 by 2 of the greatest integer function box ja by p. This is the statement of the theorem. In Gauss lemma, we have seen that this Ligander symbol is equal to minus 1 raised to the power n, where n is equal to the number of those among a, 2a, 3 and p minus 1 by 2a which give a remainder greater than p by 2 when divided by p. And now we are having that Ligander symbol a by p is equal to minus 1 raised to the power t, where t is given by summation of greatest integer function, that means box ja by p, where j vary from 1 to p minus 1 by 2. So the proof is very much similar to that of Gauss lemma, but at the end the proof will diverge and we will get a different line of action for the proof. So let us see how we will prove this theorem. So for the proof I am going to start. Consider A, 2A, or you can say consider this set A, 2A, 3A and so on up to P minus 1 by 2A. Now when you will divide these numbers by P, you will definitely obtain some remainder. Some of the numbers will give you a remainder that is greater than p by 2 and some of the numbers will give you a remainder which is less than p by 2. So let alpha 1, alpha 2, alpha m be the set of residues. Residue means remainders. These are less than p by 2, and beta 1, beta 2, beta n be the set of residues that are greater than p by 2. Definitely according to the Gauss lemma, your Ligander symbol is equal to minus 1 raised to the power n, because there are n residues which are greater than p by 2. And that is what is being stated in Gauss lemma. Now, one thing is clear, that there in this set you are having p minus 1 by 2 numbers. So the total number of remainders in these two sets will definitely be equal to p minus 1 by 2. How many remainders you are having in this first set? M, and in the second set n. So this is clear that m plus n is equal to p minus 1 by 2, because you have divided p minus 1 by 2 numbers by p, and these are the remainders you have obtained. Now look that while dividing these numbers by p, let ja when divided by p, here ja means a or 2a or 3a or p minus 1 by 2a. That means this j is a line between 1 and p minus 1 by 2. So suppose ja when divided by p gives quotient qj and remainder rj. So that means this ja can be written as p multiplied by qj, the quotient, plus the remainder rj. Now some of these rj's will be from the set of alphas and some of the rj's will be from the set of betas. Now dividing both sides by p. Dividing both sides by p, you will get here Ja by p is equal to Qj plus Rj upon p. Your Rj remainder is definitely less than p because you are dividing by p. So that means this Rj upon p is fraction and this is an integer. So of the whole number, of this complete number, this is the integral part and this is the fractional part. So Ja by p, its greatest integer function, that means its box value will be equal to Qj. So this means your Ja upon p box greatest integer function is equal to Qj. And substitute this value of Qj here. Substitute this value of Qj here. So what you are going to get here, instead of Qj, you will get box Ja upon p. This you will get. So I am going to rub the portion which I don't need now. So this expression you will get Ja is equal to p box of Ja by p plus Rj. And now take summation on both sides over j when j vary from 1 to p minus 1 by 2. So here you will have sigma j vary from p minus 1 by 2. Here this p will be outside the summation because the summation is over j, and here you will get j vary from 1 to p minus 1 by 2. And what about these Rj's? You will add all those remainders, and some of the remainders are here, some of the remainders are here, means sum of all the remainders means sum of all those alphas and sum of all those betas. So you will get sigma alpha j, j vary from 1 to m because here you are having m members, plus sigma beta j's where j vary from 1 to n. So this will be the expression when you will take summation on both sides. So I am leaving this expression here and I am rubbing the portion above it because I will not be in the need of these steps now. I will need this expression for the future calculations. I am keeping it here and rubbing the rest of the portion. Now look at these all alpha i's. They are definitely greater than 1 and less than or equal to p minus 1 by 2. On the other side, your beta j's, they are greater than p, not p minus 1 by 2 but p by 2, strictly less than p by 2. And these are greater than p by 2 but are less than p. So subtract, so multiply by minus sign first of all both sides. So what you are going to get is that minus b is less than minus beta j is less than minus p by 2, and add p to it. Adding p to it, you will get this step, and this p minus p means 0, and this p minus p by 2 means p by 2. Now your alpha i's are from 1 to p by 2 and your p minus beta j's are also from 1 to p by 2. So that means all your alpha i's and all your beta j's, they are greater than or equal to 1 but less than p by 2. That means at the most it will be equal to p minus 1 by 2. All the alpha i's and all the beta j's are between 1 and p minus 1 by 2. No alpha I is equal to beta j. Because if some alpha I is equal to beta j, that means p divides alpha I plus beta j, which is not possible because both alpha I and beta j are less than p by 2. So their sum is also less than p. And a number which is less than p is not divisible by p. We know it very well. So no alpha I is equal to any beta j. And how many alpha I and beta j total we are having? We are having p minus 1 by 2. And they are nothing but between 1 and p minus 1 by 2. So that means the set alpha 1, alpha 2, alpha m, beta 1, beta 2, beta n. This set is nothing but the set of integers 1, 2, 3 and so on up to p minus 1 by 2. So they are actually the same sets. Now, once again, adding both sides. Once again, adding both sides. First, I am going to add the right hand side. The right hand side is sigma j, j vary from 1 to p minus 1 by 2 is equal to, here I have written, sorry, beta 1, beta 2, beta n, I must have written p minus beta I, p minus beta 2, and similarly p minus beta n. So this sum is equal to sum of all those alpha i's, that means sigma alpha j, j vary from 1 to m, plus summation of all these p minus beta j's, that means sigma p minus beta j, where j vary from 1 to n. Now, what you are going to get from this step is that sigma j vary from 1 to p minus 1 by 2 j is equal to, this is your okay, I'm writing a little bit ahead, sigma alpha j, j vary from 1 to m. In the second summation, this p is a fixed number, fixed prime number or prime number p. So adding p n times, j vary from 1 to n, so you are adding p n times, so you will get np. So it will be np plus this and minus sigma beta j, j vary from 1 to n. Now, suppose this is your equation number 1 and this is your equation number 2. Now operate 1 minus 2, that means subtract 2 from 1. Subtracting 2 from 1, we will get subtracting, I am writing here, subtracting 2 from 1, we get, what we are going to get? This minus this. Here, note that this a is also a constant because summation is over j. So this a can be taken out. And now, if you subtract this term from this, sigma j, j vary from 1 to p minus 1 by 2 is here and it is here as well. So you will get a minus 1 times. So you will get a minus 1 times sigma j, j vary from 1 to p minus 1 by 2. This is on the left hand side. On the right hand side, this is np and this is also p times something. So p can be taken out. So it is p common and within the brackets you will get sigma ja upon p greatest integer function. Sorry, I have used the Leander symbol function in fact. Greatest integer function j vary from 1 to p minus 1 by 2 and minus n this from this step. Now this will be cancelled out because you are subtracting and this will be added. So adding this you will get 2 times. So you will get plus 2 times sigma beta j, j vary from 1 to n. Now we know that if two quantities are equal, then they are congruent to each other modulo any number. So they are congruent to each other modulo any number. So I am taking they are congruent to each other modulo 2. I am taking just modulo 2. Let us see what happens if we take modulo 2. This a minus 1, a is odd. So a minus 1 is even and even number divided by 2 will give you the remainder 0. So this a minus 1 will be replaced by a 0. So this will be replaced by 0 because a minus 1 is an even number and even number divided by 2 will give you the remainder 0. Similarly, p is also an odd integer. P is also, this 2, look at this 2. Now this 2 will also be 0 because it gives the remainder 0. So what you are going to get is that p and sigma ja by p, j vary from 1 to p minus 1 by 2 minus n is congruent to 0 modulo 2. Once again, this p is an odd prime number. And odd prime number, any odd integer when divided by 2 will give you the remainder equal to 1. So this p can be removed by 1. And 1 into anything, we know that it is the same. So this is the same quantity, sigma this and this. Now, take this minus n to the other side, you will get this is congruent to n modulo 2. If two numbers are congruent to each other modulo 2, then either both are even or both are odd. Because an odd number cannot be congruent to an even number modulo 2. Suppose you are taking 2k plus 1 is congruent to 2m modulo 2. That means 2 divides 2 times k minus m plus 1, which is not possible because 2 times something plus 1 is an odd number and 2 divides odd is absurd. It is not possible. So two numbers are congruent to each other modulo 2 means either both are even or both are odd. Whether they are both even or they are both odd, minus 1 raised to the power this number is equal to minus 1 raised to the power this number, because if both are even, both sides will be equal to 1, and if both are odd, both sides will be equal to minus 1. So that means minus 1 raised to the power n is equal to minus 1 raised to the power sigma j vary from 1 to p minus 1 by 2 greatest integer function j a by p. Now what is minus 1 raised to the power n? N is the number of those numbers among a to a 3 up to p minus 1 by 2a which give remainder greater than p by 2 when divided by p. So minus 1 raised to the power n, according to the Gauss lemma that we have proved in the previous video, this minus 1 raised to the power n is equal to the Ligandr symbol a by p. So this is the Ligandr symbol a by p. So a by p Ligandr symbol is equal to minus 1 raised to the power t, where t is summation j vary from 1 to p minus 1 by 2 of the greatest integer function, or you can say box j a by p. So this is what we have proved in this theorem. What we were required to prove, we have proved. So this was an important theorem which will be used a lot when we will be moving ahead in several questions. And one of the applications of this theorem you can see is in the form, you can say it is a theorem, a question, a problem, anything. So I am naming it as a problem. Prove that Ligandr symbol 2 upon p is equal to minus 1 raised to the power p square minus 1 by 8. This we will prove now. So in the previous theorem, when we were proving, we had a step that I am going to repeat. The step was a minus 1 sigma ja upon p, if I am not forgetting, p j vary from 1 to p minus 1 by 2 is equal to I think I have written a little bit wrong. It is JA, sigma JA. In the previous theorem, you can check, it is JA is equal to P times sigma box JA by P, J vary from 1 to P minus 1 by 2 plus sigma all alpha j's plus sigma all beta j's. I think the next step, sorry, this is actually minus n minus this, or okay, so this was p times n minus this or this minus n, np. So either it is n minus p or p minus n minus this, and plus 2 times sigma beta j, j vary from 1 to n. This was the step, I think so. Now for this question you are having 2 upon p. That means your a is equal to 2. So substitute a is equal to 2 here. So substituting A is equal to 2 here, we will get 2 here. We will get 2 here, 2j by P. Here I am not substituting, so you can have, no, sorry, in fact A was not there. A we have taken outside. So this is like this. Now, this 2 minus 1 is 1. Okay, this is 1. This 2j upon P. The maximum value of j was P minus 1 by 2. So what is the maximum value of 2j is P minus 1. And P minus 1 divided by P is a fraction. So the largest of these 2j by P is a fraction. That means each of these 2j by P is a fraction. And for a fractional number, the greatest integer function, the box is 0. So this whole quantity is going to become 0. So what you are going to get is sigma j vary from 1 to P minus 1 by 2 is equal to minus Pn plus 2 times sigma beta j vary from 1 to n. And now you take both sides congruent to each other, modulo 2. Modulo 2. Modulo 2, your minus P will be 1. So you will get n plus this. Or I think in the theorem it was n plus or n minus. I am not remembering it. Either it was plus or it was minus. I think it was minus here. In the previous theorem, there was a minus sign which I have mistakenly taken as plus sign. So minus this sign. Now, this 2 times beta j is also equal to 0 because you are taking modulo 2. So this quantity is also going to be 0. So here n is congruent to this now. That means n is congruent to, this is the sum 1 plus 2 plus 3 plus up to P minus 1 by 2 modulo 2. That means your n is congruent to this sum is equal to P square minus 1 by 8 by using your sum of arithmetic progression modulo 2. That means, now once again, they are congruent to each other modulo 2. That means either both are even or both are odd. Whether they are both even, whether they are both odd, minus 1 raised to the power, both these numbers will become equal. Even if they are equal, even if they are even if they are odd. Minus 1 raised to the power n will be equal to this. But minus 1 raised to the power n is the value of Ligander symbol a by p. So Ligander symbol a by p, that is minus 1 raised to the power n, is now equal to minus 1 raised to the power p square minus 1 by 8 because n is congruent to p square minus 1 by 8 modulo 2. So your a by p. But what was a? Your a in this question was 2. So therefore the Ligander symbol 2 by p is equal to minus 1 raised to the power p square minus 1 by 8, which is a very important application of the previous theorem that we have done. Further, another thing is to be observed. What we have just proved now is that the Ligander symbol 2 upon p is equal to minus 1 raised to the power p square minus 1 by 8. Your p is odd prime. So there are 4 cases. Either your p is 8k plus 1 if it gives remainder 1, or it is 8k plus 3, or it is 8k plus 5, and 8k plus 5 means 8k minus 3. And similarly, your p can be 8k plus 7, and 8k plus 7 means 8k minus 1. What will happen in all these cases? If your p is 8k plus 1, you substitute it here. So what is your p square minus 1 by 8? P square is 64k square plus 16k plus 1 minus 1 and divided by 8. So this will be even number. Clearly, because 2 can be taken out. For the second case, your p square minus 1 by 2 will become 64k square plus 48k plus 9 minus 1 upon 8, and it is odd number because from this portion you will get even plus 1 additional will give you odd. So this is even, this is odd. Similarly, in this case, you will once again get odd, and in this case, you will get even. And even means the Ligander symbol is 1. The odd means the Ligander symbol is -1. So that means the Ligander symbol 2 upon P is further equal to 1 if your P is congruent to, now these two cases, your P is congruent to plus minus 1 modulo 8, plus minus 1 modulo 8. And similarly, from these two cases, your 2 by P Ligander symbol is -1 if your P is congruent to plus or minus 3 modulo 8. So this is more simpler result regarding the Ligander symbol 2 by P. So I'm going to stop this video here, move on to the questions based on these theorems or these problems, and then in the next video I'll move on to the next topic, that is quadratic reciprocity law. Till then, thank you once again.